So a common thing in modern data analysis and any kind of computational is you have a computation that's too complicated or the data set is very large. This happens especially in a lot of people presented biological research. You have many genes. And it also happens in large language models that you can't store everything on one computer. So the idea is you want to cut it up into some pieces so that things can be done in parallel at the same time, concurrently. And you can recreate create the task from the pieces. So the main problem is, so one of them can go slower than the others, and you want to somehow give it in such a way that if one of them crashes, goes slower, or anything goes wrong with it, even if just the connection is lost, you can recreate both things. Right? So I start with the simplest possible example. It's a very simple matrix multiplication, and the idea is you can cut it up in such a way that each one of these machines can do it in parallel. And the reason this can be done is because matrix multiplication is linear in its first argument, so that this A1b and this A2b can be done independently of one another. Now, a lot of people will say, okay, well, why use coding theory? A lot of people, especially in the math community, people come up with complicated problems just for the sake of it. It's a bit of a competition, really. Well, actually, in here, it's it actually you're using resources more efficiently. So the idea is if you tried something very naive, like just replicating, just repeating the same thing twice, it would be an inefficient use of resources. So in here, you can see that to be able to cover the failure of A2B failing, you need at least another copy of A2B in order to complete the task. But if you use coding theory, maybe take my word on it, the distributivity property of matrix multiplication gives you that if you wanted to solve for M2 here, you could subtract M1 from M3, and then I can use 3 machines. Now, sometimes people ask, well, I don't care, I have 4 machines, right? Well, okay, well, you have 4 machines, I still am more efficient when I use coding theory, because now if you give me an extra machine, I can tolerate more failures. So in here, even in the scheme, you could see I can fail the 2 copies of A1B, and the whole thing fails. Whereas in the right-hand side, I can still solve for A1B, for example. You'll have to take my word that all the possible combinations of 2 lawyers will solve it. And this, for some people, this may look familiar. So this is very much looks like a classic problem all the way back to Claude Shannon. Most people know who Shannon. He's like the only person from my field that people from other fields know. Pretty famous scientist. And the idea is we want to encode it. If you saw the previous slide, there's some kind of encoding procedure. Then you have a channel where things fail. And then you want to be able to design the thing so that any K subset will recreate the thing, right? Well, the thing that differentiates my research from error correction on CD-ROMs or telephone calls or hard disks and things like this is that the message that goes in is not equal to the message that goes out. So there's some kind of dynamic procedure, there's some kind of information processing. So usually on a telephone, the thing that you say, hello goes in, hello goes out. And my thing, some function and some data goes in, but what comes out is the function applied to the data. And I like to show slightly more complicated examples little by little to see how complicated. So I can start slicing the matrix A and slice the matrix B, and it gets a little more complicated. But someone came up with the optimal scheme for that. Agostino and Maudali. They found a way to multiply 2 things so that the product is a nice code, in particular Reed-Solomon code. And this is a thing that's pretty common in engineering. You have something that's complicated, for example, A times B, you transform it into some other domain. So usually in electrical engineering, it's time and frequency. In here, it's quite similar. It's like something that is resilient to noise. And I need that the product of the two things is a larger cause. And then, so I like to end it with I don't think the point is not to understand the slide, but just to show that when I finally completely slice A and completely slice B, I sometimes call this the 3D case. It becomes quite complicated. So there's a famous result in the computer science that the most optimal non-noisy version of this requires 7 multiplications, but currently we only have a scheme that does 9 multiplications. And this is part of something more general, where this is one of my favorite results, that actually this research relates to a very classical problem that's often standing and people worked on very long, which is matrix multiplication. Finding the best exponent well, I think it's a very interesting problem. And of course, it's very important because basically all modern data analysis is done on GPUs. So whenever you use ChatGPT, whenever you do your data analysis, you're probably using GPUs to speed up, and that's all matrix multiplication. So yeah, technically.